Okay, today's lesson is 6.8, I do believe, on the cosine law. So learning goal for today is after this lesson, I can use the cosine law to solve for missing side lengths and angles in triangles. So similar to the sine law, this works with non-right angle triangles, and one version of the cosine law works for a missing angle, and the other works for a missing side length. So a couple things we have to recall. Primary trig ratio, sine, cos, and tan, can only be used if you have a 90-degree angle in your triangle. So they work for right angle triangles. So does Pythagorean theorem. Then if we take a step further, if we don't have a right angle triangle, last lesson we learned the sine law. But it can only be used if you have a complete ratio. And if you don't understand what I mean by that, you need to go back and rewatch the sine law lesson from last class. And by a complete ratio, I mean of our A over sine A. So you have the top and the bottom. You have a numerator and the denominator, or you have the angle and its opposite side. So let's say we had a 16 centimeter side across from a sine of 42-degree angle. So that would be a complete ratio. And that'll work if you use the sine law. But then we have to take a look at a triangle where we don't have a complete ratio. We'll get into some specific examples in a minute. First, we're going to do a little proof for the cosine law, just like how we did a little proof for the sine law. So what happens when we can't use either the sine law or SOHCAHTOA? So I'm going to draw a random triangle. It's not equilateral. It doesn't have a 90-degree angle in it. Just triangle looks something like that. Let's label our vertices A, B, and C, angle A, B, and C. So then obviously our opposite to angle A, we have side A. Opposite to angle B, we have side B. And opposite to angle C, we have side C. I'm going to do a little drop down here, similar we did in our last proof. I'm going to draw a height of this triangle. So we know the height meets the base at 90 degrees, so that's a 90-degree angle. So we're creating a little right angle triangle that we can use SOHCAHTOA in our proof of this large triangle. So the first triangle I'm going to take a look at, let's highlight it in orange so we can see here, is this small triangle. It's got a right angle in it off to the right. A couple things we know, a couple things we don't know. This height, let's label that H. And then we have this little base down here. I'm just going to call this little base X for now. It's not obviously the full length of B. X is less than B, but it's a little chunk out of side length. B is side length X. So we're using the cosine law. So I'm going to use cosine to start here. I'm going to say, okay, if we're looking at the cosine of angle A, that is equal to SOHCAHTOA, is the adjacent over the hypotenuse. So my adjacent in this case is X, my hypotenuse is C. So we've got X divided by lowercase c, that is side length C. Or I could do a little bit of rearranging there, and I could say C times cos of angle A is equal to X. It doesn't look like I can go much further from there. I don't know a value of X, don't know a value of C, don't know a value of A, angle A. So I'm just going to call that number 1. I'm going to set that off to the side, and I'm going to use it in a minute. Then if I take a look at this triangle here of side lengths X, H, and C, I can also do the Pythagorean theorem to potentially solve. So I know that X squared times, or plus H squared will be equal to C squared. So X squared plus H squared will be equal to my hypotenuse squared. We can see from that little triangle. I'm going to rearrange this ever so slightly and say, well, H squared is then equal to C squared minus X squared. No particular reason, but I'm going to call that number 2. I'm just going to set it off to the side for now, and we're going to come back. We're going to substitute in for that value. But that's all about all I can do with that little triangle. So I'm going to take a look at my next right angle triangle I have here, slightly bigger one in this particular case in red, involving angle C. A, H, And then if we take a look at this last measurement here, the base of this triangle, well, if this full thing is B, this full side is B, then this side length right here, from here to here, this must be B minus X from here to here. So we've got three sides to this right angle triangle. Make no mistake, that height does make it a right triangle. So I'm going to do a little Pythagorean theorem here. And I'm going to say, well, h squared plus my base, which happens to be this ugly thing, b minus x squared, is equal to my hypotenuse squared, a squared. And that's the same as saying a squared plus b squared equals c squared, where that c is your hypotenuse. In this case, a is my hypotenuse. So if we take a look at what to do here, I can see that b minus x is actually h squared plus b minus x times b minus x is equal to a squared. So if you're an arrows man, you can draw in your arrows here. And let's start distributing this. We've got h squared is equal to b times b is plus b squared, b times minus x, and minus x times b is minus 2 bx's. And then last but not least, minus x times minus x is positive x squared is equal to a squared. So then, let's take a look at what substitutions we know. I know that x is actually equal to c times cos A, and I know that h squared is actually equal to c squared minus x squared. So if I look at this first h squared here, I'm going to sub in number 2. So I'm going to even write that title, sub in 2. And 2 being that h squared is actually c squared minus x squared. So I'm going to write here c squared minus x squared, because that's taking the place of h right there. Then we've got plus b squared minus 2bx plus x squared is equal to a squared, which looks a little big and ugly, but let's take a look and try to clean this up a little. We've got a minus x squared here. We've got a positive x squared here. Obviously, those two add to 0. So I'm going to rewrite this as, I'm just going to flip sides here so I can see what I'm working with. A squared is equal to b squared. That's right there. My x and my x squareds are both eliminated, plus c squared minus 2bx. So I've taken care of my c, I've taken care of that, I've taken care of all my terms there. My a, I just wrote on my left side to make it a little clearer to myself. Then we have this x right here. And we can see in equation 1, we know what x is. X is actually c times cos A. So I'm going to write another title in and say sub in number 1. So this equation is going to be a squared is equal to b squared plus c squared minus 2b. And then instead of writing x, I'm going to write in c times cos A. So this is times c times cos of A. And this right here is the not Pythagorean theorem. This is the cosine law. Put a big square around it, highlight it, do what you need to do. Couple things we need to know about the cosine law. Well, it looks big, ugly, and confusing. It is just the Pythagorean theorem we can call it Pythagorean theorem for a non-right angle triangle. So we can use it to solve in a non-right angle triangle. And we can see bits and pieces of it look very familiar. A squared equals b squared plus c squared. Looks a whole lot like the Pythagorean theorem. And that most important, I'll write it in these boxes down here, the most important thing you get right with the cosine law is that the angle matches up to the side on the left-hand side of that equation. So what I mean by that is, see how this is side length A? Actually, let's do this in another color to make it stand out a little. This is side length A. Notice how that matches angle A written right here. So the angle and the side need to match each other. The B's and C's in the middle, not as picky about what they are. But as long as that angle matches that side, they're across from each other in the triangle. So another way to write this out, let's say you had a triangle that had PQ and R in it. So let's say we had a triangle PQR. Then if P squared was on that side of the equation, then it would be Q squared plus R squared minus 2 times Q times R times the cosine of this one right here has to be angle P. So it has to be across from that side. So if you forget anything else, everything else from cosine law, remember that that side and angle need to be matched up to each other. So we'll go through some examples if this is making a whole lot of sense, and we'll see how we can actually use this formula. A couple things we do need to know: cosine law can be used when you have three sides and want to find an angle. So if I gave you a triangle here and I said this side's 7, this side's 11, this side's 22, and asked you for this angle, we could use cosine law to solve for that. We've never been able to do that before, which is kind of interesting. If we're given three angles, we can't solve for a side though. And it can also be used when we know two sides and the angle we want to find, and the angle between, and we want to find the third side. I like to call this a contained angle. What I mean by a contained angle is, let's say I've got a triangle, it looks something like this, no right angles, not equilateral, ugly looking triangle. A contained angle means you know both the sides on beside it, both sides adjacent to it. So let's say this is angle 33 degrees, no particular reason. Then if we know this side up here, let's say this is 13, and let's say this is 17. See how that angle is kind of squished in between two sides? We can't use sine law for this. I'm going to show you why, but we can use cosine law for this, and I'm going to show you how. And we'd be able to solve for a missing side. Let's say we wanted to solve for that side over there. So those are the two times we're going to use cosine law. Cosine law is a little bigger, a little uglier than our sine law. It takes a little bit more work, and there's a little bit more room for error. So if we don't have to use cosine law, okay, if we can use sine law, we always use sine law. It's just quicker, easier, less room for error. But there's certain circumstances that we have to use cosine law. So if we look at this first triangle, we kind of check to see, can you use sine law? AKA, is there a complete ratio? So I'm looking at P and side length P, lowercase p down here. See how this is not a complete ratio. We would have P over sine P. So we would have P over sine 70. It's not a complete ratio. When using sine law, we have to have a complete ratio. Clearly, we don't know this angle. So R, angle R inside R wouldn't make a complete ratio. Clearly, we don't know this angle. So Q and side length Q wouldn't be a complete ratio either. So we would have to use cosine law on this one. Cosine law, because there's no complete ratio. Next one. If we look at this triangle over here, we have a complete ratio. There's no letters on the side of this. So let's say I call this angle A. This is equal to side A. We have a complete ratio. We can say A over sine A, which happens to be 37 here, is equal to, our next ratio will be X over sine 79. I'm not going to go ahead and solve this, but we could solve for this. So we substitute A being 13. We have 3 of the 4 missing pieces of the puzzle, and we could just use sine law. So this one we would definitely use sine law. Always use sine law when you can. Just makes your life a little easier. And then last but not least, they're trying to trick us ever so slightly here. You can probably see their trick. But that angle C is just going to be 100 minus 42. 180, sorry. Minus 42. Minus 75. We have 63 degrees here. So then we have a ratio. We have an angle and its opposite side. So we could set this up as angle C over side C. So 22 over sine 63 is equal to either one of these ratios. Let's say we wanted to solve for this side first. So that would be our next ratio. We would have over B over sine 75. And we could solve for B. I'm not going to go ahead and do that, but if you really wanted to, you could go ahead and solve. So we can see when to use the cosine law and when to use the sine law. If you have a complete ratio, use the sine law. If you don't have a complete ratio like this one, then you have to use the cosine law. So let's try one example out here. Example 1, an acute DEF, so no obtuse angles in this, all angles are less than 90 degrees. We have DEF. I'm going to draw it a rough triangle there. Clearly it's not going to be to scale. These are some pretty precise measurements here. But I just want a triangle that isn't necessarily equilateral and does not have a 90 degrees in it. I'm going to call this DEF. And we're going to say a side length D. So across from angle D is 4.9 centimeters. Side length F, so across from angle F over here is 6.2 centimeters. And then angle E, so this angle here is 64 degrees. So this is what we call a contained angle. Contained angle. Hence that angle that we know is sandwiched in between two sides that we know. Both sides adjacent to the known angle are known sides. And as soon as you see a contained angle, we have to use cosine law. We cannot use sine law because there's no complete ratio. If you try to set up one of your complete ratios of sine law, you won't be able to do it. So let's try cosine law here for the first time. So I'm going to set this up as E is my known angle. So E is my known angle. I'm going to set this up to solve for the opposite side of my known angle. So I'm going to rewrite the cosine law. Clearly I don't have A, B's, and C's here, but it doesn't really matter what the letters are. E is my unknown side length. And I know opposite on the very far end of this equation, approximately that much room it's going to take me, has to be cosine E. So those two letters need to match. One needs to be a capital, one needs to be a letter. Hence they are opposite each other here. You can see in that diagram. It's always going to be the cos for cosine law. Now your other letters in here, it doesn't matter really what order we write them out. D squared plus F squared minus 2D times F times the cosine of E. So we can start filling in some values we know and we don't know and see what we solve for. E squared, I don't know what E is. That's our unknown. Side length D is across from angle D, is 4.9 squared. Plus F, which is across from angle F, 6.2 squared, minus 2 times D, which is 4.9, times F, I just put those in brackets to clean it up a little, 6.2, times cosine of E, cosine of 64 degrees here. So this becomes some calculator work. I'm going to try to keep this as accurate as possible. So without typing these in and writing out a decimal answer and then trying to take the square root of that, I'm going to get my calculator to do all the work for me. So if I want to solve for just e, technically it's positive negative here, but we're talking about side lengths of a triangle, so I'm not going to bother with the negative version of it. And I'm going to take the square root of this full thing, 2 times 4.9 times 6.2. See how this gets a little messy without brackets? I'm going to put some more brackets around there. Doesn't make any difference, but just helps me read it. Cosine of 64. So I'm going to try to type this all into my calculator in one go. Depending on your calculator, you may need to break this up into bits and pieces. Hit enter and use the answer key or answer sign there. It's going to help you out lots. So I'm going to do square root of this whole thing is going to be in brackets 4. I'm going to put this whole thing in brackets 4.9 squared, I do believe it was. Let's see how good my memory is. Squared, there's my squared button, plus 6.2 squared minus 2 times, calculator does a little dot, 4.9 times 6.2 times cosine of 64 degrees. So you can see my calculator is pretty good. It gives me that full line of feedback. You're welcome to download this calculator if you don't use it. It's the Desmos Scientific, not Desmos Graphing, but Desmos Scientific. It's a nice graphic calculator, or a nice calculator, scientific calculator to use. If you've got a nice calculator that gives you one line of feedback, just always use that same calculator. You'll get better and better and better with your own calculator. And I get the answer of 5.9845. Let's see what the question wants us to round to. E equals 5.98. Can't read. And round measures to the nearest degree or tenth of a centimeter if necessary. So it does want us to round to tenth of a centimeter because we're working in centimeters here. And so we would round that to approximately 6.0 centimeters. And there's using the cosine law to solve for a contained angle. So notice that angle was contained, and we solve for the opposite side. So E is 5.98. So then we only ever have to use, almost always, use cosine law once per question. Once you've solved for this opposite side, 5.98 approximately, then we can go back and use cosine law. So now if we want to solve for a missing angle, we can go back and use this complete ratio we just solved for, and a side and an unknown. So let's say I want to solve for angle D next. So if you remember your cosine law or sine law from last lesson, you always need a complete ratio and then your unknown on the numerator of the other ratio. So my unknown is sine D. So I'm going to set up my equation of sine D over side length D is equal to a complete ratio. Well, my complete ratio now that I've solved for it is going to be E over side length, sine E over side length E. So we can fill in some values I know and I don't know. I don't know angle D. Side D is 4.9 is equal to sine E, which is sine 64. Divided by 5.98. I'm going to use the non-rounded version, be a little more accurate here than rounding it to 6.0. And then I have to solve for a missing angle. So I'm going to multiply both sides by 4.9. Once again, if you're unsure what I'm doing here, make sure you've gone back and done sine law. You need to be comfortable with sine law here. Sine 64 divided by 5.98. And then we're going to take the sine inverse of this to eliminate a sine to isolate for that angle D. We need to use the inverse function. So we have got 4.9 times sine 64 divided by 5.98, and that's calculator work. So we can do sine inverse. Once again, my calculators can handle all this in one function. Your calculator, you might have to do bits and pieces of this. So that's 4.9 times sine 64. 4.9 times sine 64 and bracket. And this whole thing is going to be divided by sine, 5.98. 5.98. You can see in my calculator, it just divided the sine 64 by 5.98, then it times it by 4.9, which is fine. BEDMAS, that division and multiplication doesn't matter. 4.9 is technically over 1, so it's multiplied by the top. So that would be 47.43. So we get the answer for D of 47.43. 1.5, yep, so we can leave that as that. That is an angle measurement in degrees. So we can see it wanted to round to the nearest degree. So it wanted us to round quite a bit. So the nearest degree, we would clearly round down to 47 degrees. There would be accurate enough for this question, approximately. And next one there, we have angle F would be our last remaining one to solve for. F right here. And we can see clearly angle F is going to be equal to 180 degrees minus our 64 we got from before, minus 47.73. Let's use our more accurate one until the final answer, round in the final answer. And we do 180 minus 64 minus 47.43. Get the answer of 68.57. 68.57. And of course that's in degrees. So angle F is equal to 68.57. Then the question wants us to round to the nearest degree. We should make these round, make sure they round or add to 180 degrees, but they are rounded ever so slightly. So we're going to say this rounds up to 69 degrees, and that of course is going to be approximately. So we can see, due to our rounding errors, 64 plus 47 plus 69, we're a little above 180 degrees there. That's fine. That's just because we rounded so heavily there. That's why we have that approximation. So that is using cosine law to solve for a side length. So we solve for cosine law to solve for angle or side length E, and then just use sine law after that. So we only need to use cosine law once to get that complete ratio, then use sine law. So we'll try a slightly more challenging one here. This one we're going to solve for an angle measurement. And we know when solving for an angle measurement in both SOHCAHTOA and sine law, it involves that inverse trig function. So once again, cosine law, we're going to have to use that inverse function again. Okay, so we have in an acute triangle ABC, a little triangle means triangle in this case, doesn't mean delta, is triangle ABC. So let's label this A, B, C. And A is 14. So that's across from angle A, is side length A. B is 17. Across from angle B is 17 centimeters. And C is 16 centimeters. So across from C is 16 centimeters. And it wants us to solve triangle ABC. So it wants us to find all three missing angles. In this case, it wants all angles and all sides. It gave us all angles, so we're going to solve for, or it gave us all sides, so we're going to solve for all angles. So I'm going to pick a random angle to solve for first. Actually, not so random. Let's go alphabetical here. So let's solve for angle A first. So if we notice, we don't have a complete ratio, so we can't use sine law. So if I want to solve for angle A first, we have to set up that equation properly. So if A squared is here, then on the far side of this equation is going to be cos of A. We can fill in the missing values here. We can fill in b squared plus c squared minus 2bc times cos A will be that equation we're going to use. Let's say I happen to not solve for A first. Let's say I happen to try to solve for C first. So if I was setting up this equation to solve for angle C, then it's important if I have angle C on this far side, cosine of C, that it matches up to whatever letter or side length is on the left-hand side of this equation. Then the other letters don't matter too much. I'll go alphabetical order. A squared plus b squared minus 2 times a times b times cos C. Does that make sense? You can see how I could do this the third time for b as well, but I'm not going to. So let's solve for angle A first. So if we take a look at this, we can fill in what we know, what we don't know. A is 14 squared, plus B, which is 17 squared, plus C, which is 16 squared, minus 2 times, put a little time symbol there, 2 times B, which is 17, times C, which is 16, times the cosine of A, where A is our unknown. We don't know that angle A. So it takes a bit of rearranging here. You can type this in your calculator, and you can fill out numbers because, 14 squared, 17 squared, 16 squared, they're all whole numbers, so we wouldn't have to round anywhere. I'm going to show you the next 3 steps. I understand if you don't show all these steps every single time, if you kind of get used to it and skip some steps here, but I'm going to show you each one at a time. So first thing I'm going to do is I'm going to bring over my 17 squared and 16 squared. So I'm going to subtract 17 squared and 16 squared from both sides. So I'll have 14 squared minus 17 squared minus 16 squared is equal to minus 2 times 17 times 16 times cosine A. Excuse me. My next step is this minus 2 times 17 times 16. It's just a number. It's like saying, I don't know what number that is. It's a big number. Multiplied by cosine of A. I could type this into my calculator and get the actual number here, just because those are whole numbers. Sometimes they're ugly decimals, and I won't want to write them all out, so I'm going to show you the actual work. So we're going to divide both sides. We're going to divide the right and left-hand side by, let's do this in another color so it's not so confusing. Divide this by minus 2 times 17 times 16. If we divide that side, those two will cancel out. And if we divide one side, we have to divide the other by minus 2 times 17 times 16. So we're going to have 14 squared minus 17 squared minus 16 squared divided by minus 2 times 17 times 16 is equal to cosine of A. Once again, this is just number. We could write out the actual number there. I'm just showing you all the math without using my calculator. Then I'm going to type it all in at the end. We could throw this into your calculator and get an answer halfway through, of course, which would be fine because it wouldn't be too ugly of a decimal. We wouldn't have to round it. And now if I want to isolate for A, I want to get cos off of A. We know to isolate for an angle measurement, you have to take the inverse function. So this is all going to be cosine inverse of 14 squared minus 17 squared minus 16 squared, all divided by minus 2 times 17 times 16. Whew, that was quite a bit. So some of your calculators are better than others. Once again, you may have to type this in as a numerator divided by denominator, hit enter, So that answer saves in your calculator, then do cosine inverse of answer. I'll do it that way just to show you. So we're going to do 14 squared minus 17 squared minus 16 squared is equal to, that's my numerator. Then I'm going to do my numerator, my answer, divided by my denominator. My denominator was minus 2 times 17 times 16, minus 2 times 17 times 16. I'm going to hit enter. That saves it in my answer button in my calculator. Then I want to do second function, the cosine inverse of that answer. Hit the answer button, saves it in my calculator. And we get the answer of 50.092. 50.09 rounded to 2 decimals. 50.09 degrees is equal to A. And round measures to the nearest degree if necessary. So rounded to the nearest degree, we would say angle A is approximately 50 degrees. Round it. Put a box around that one. Reader knows where that answer is real quick. So we've solved for one of the angles. We could do the exact same thing using C, using this equation off to the right-hand side in pink. Or we could, since we already have one angle and its opposite side, we have a ratio now. We have a complete ratio, so we could use sine law. So I'm going to go ahead and use sine law. If you want to use cosine law again, you want some more practice, go ahead, pause the video, use cosine law. I'm going to do a slightly quicker route by using this complete ratio. So now that we have angle A being 50 degrees, our complete ratio is going to be sine A over A, and then we can solve for, let's go B next for no particular reason, sine B over B. So this will be our next ratio we're going to use here. So my unknown is going to come on the numerator on my first one, and I'm going to have sine B, I don't know what that is, divided by B, which is 17, is equal to my complete ratio. My complete ratio is what I just solved, is going to be sine A. I'm going to use sine of 50.09. Let's keep that little bit of extra accuracy in there. Degrees divided by opposite of that is side length A is 14. Then we can use some sine law to solve for a unknown side. I'm going to multiply both sides by 17. If you're getting good at this and you skip a step, that's just fine with me. I'm going to show this line of work. 14. Then I want to isolate for B, get B all by itself. To get rid of this sine that's attached to B, you take the sine inverse of both sides. 17 times sine of 50.09 divided by 14 to solve for that angle measurement of B. So calculator work here. Once again, my calculator is pretty swift. It can do this all in one step. So that's going to be the sine inverse of 17 times the sine of 50.09 degrees, and all that's going to be divided by, 14. Once again, you kind of see on my calculator there, it looks like it's just dividing sine 50.09 by 14, but that 17 is just over 1 and is being multiplied by the numerator. And we get the answer of 68.657 or 68.66. 68.66 degrees, rounded to the nearest whole degree, is going to be 69 degrees even. So then we can find out our third measurement by simply doing our 180 minus minus. So our third measurement will be angle, let's see here, what did I solve for? Angle C. So angle C is going to be equal to 180 minus, let's go a little more accurate, let's use 50.09 minus 68.66. Use a calculator for this one. 180 minus 50.09 minus 68.66, and we get 61.25 degrees. So angle C would be equal to 61.25 degrees. Rounded to the nearest whole degree, angle C is going to be 61 degrees there. So we can see, oh, this one adds up a little nicer there. We get exactly 180 degrees with our rounded values. Any questions there? Just ask away in class or email your teacher on that one. We're going to do one more problem for today, and that's a word problem where the diagram in this one has been drawn out for you. But a lot of these problems you'll have to draw the diagram eventually. We'll get to that. So example 3 is a third road is planned that will directly connect Brookside and Highcliffe, which are about 16.5 kilometers apart. So this is the new planned road here, 16.5 kilometers. Find the angle to the nearest degree between the new road and the existing road from A, Rolling Meadows to Brookside. Rolling Meadows to Brookside. So this is the existing road, Rolling Meadows to Brookside, and they want the angle between the new road and that one. So essentially they're looking for this angle. Let's call that theta A. We're going to solve for theta A is what we're looking for. So we want to solve for an angle in a triangle that we don't know any angles in. So we're going to have to set this up using cosine law to solve for a missing angle. Just to clarify, I'm going to use B for Brookside, I'm going to use H for Highcliffe, and I'm going to use R for Rolling Meadows. That might make this a little easier. So then this 15 will be lowercase b, lowercase h will be 10, and 16.5 will be lowercase r, just so you know what I'm talking about there. So if we want to solve for that angle, theta A, that's essentially what we're saying is solving for angle B, capital B. So when we set up this cosine law equation, we have to have angle B as the measurement on the far right-hand side of this equation. So that means side length B needs to be on the left-hand side of this equation. So when we set up our equation, it's going to look like this, with our other two letters in the middle. Doesn't really matter which order we put our letters in. Let's go HR, alphabetical. H squared plus R squared minus 2 times H times R times cosine of B. Looks like a lot of letters here, but we can start to fill in what we know, what we don't know. B is equal to 15 squared. H is equal to 10 squared. R is equal to 16.5 squared minus 2 times 10 times 16.5 times cosine of B. And this is what we're trying to solve for, right? That's our unknown, is that capital letter B. So I'm going to show some lines of work here. I understand if you're getting the hang of this, if you don't show all these lines of work, that's fine. But I'm going to bring my 10 squared and my 16.5 squared over first. 10 squared minus 16.5 squared is equal to minus 2 times 10 times 16.5 times the cosine of angle B. Next, I'm going to divide both sides by minus 2 times 10 times 16.5. So I'm going to have 15 squared minus 10 squared minus 16.5 squared divided by minus 2 times 10 times 16.5 is all going to be equal to cosine of b. Now to isolate for this cosine of b, I'm going to move cosine over to the other side. So we have to take the inverse of this. So if I take the inverse of here, I'm just going to write it right here to save myself one line of writing that same stuff over, is going to be equal to b. Make that a little closer. So now it becomes some calculator work. We have to type that in. And once again, everyone's calculator is a little different. I'm going to type this all in one line so you can see how handy this Desmos calculator can be. So this is going to be the cosine of 15 squared. What is it? 15 squared minus 10 squared minus 15 squared minus 10 squared minus 16.5 squared. So that's my whole numerator. So you notice I got my whole numerator in brackets, and I'm going to divide that by my whole denominator, which is going to be minus 2 times 10 times 16.5. And then I can end bracket this whole thing. And I took the cosine inverse of that whole thing. So we get the final answer of 63.499 or 63.50. So B is going to be equal to 63.50 degrees there. So we could write a little therefore statement. Therefore, the angle between the new road and the road from Rolling Meadows to Brookside, that angle A, or theta A, or capital B, is equal to 63.50 degrees. Then, next one, part B says, what is the angle between the new road and the existing road from Rolling Meadows to Highcliffe? So now they're saying, okay, what's the angle between the Rolling Meadows to Highcliffe and the new road? So that'll be that angle right there. So what they're really asking there is, what is that angle, theta B or capital H in our case? They're asking you to solve for capital H in this diagram. Now, since we have just solved for angle B, we have a complete ratio. We know angle B and side length B. As soon as you have a complete ratio, it's much easier to use sine law than it is to use cosine law. So instead of using cosine law again, I'm going to use sine law to solve this because we have that complete ratio. So I'm going to say h is my unknown. So I'm going to say sine h is in my numerator. It's very handy to have your unknown in your numerator when using sine law. Divided by side length h is equal to, I'm going to use my complete ratio. In my case, I called this sine b for Brookside over side length b. So we can fill in some values. We know, we don't know. We don't know capital H. So that's what we're trying to solve for. We know the side across from it is 10. We know sine b. We just solved for that. That will be the sine of 63.50 degrees. And we know the side opposite to sine b is 15. So we can solve for this one by isolating for h. We're going to multiply both sides by 10. So I'm going to have sine of h is equal to 10 times sine of 63.50 divided by 15. Then we're going to take the inverse of this. So I'm going to show that the sine inverse is equal to 10 times, or the sine inverse of 10 times sine 63.50, all divided by 15, is equal to h. A little bit of calculator work here. Saying second function sine inverse of 10 times sine 63, 10 times sine of 63.5 divided by 15 is equal to 36.628 or 36.63. Oh, 36.63, not 36. And I do believe I read this earlier. They wanted it rounded to the nearest tenth of a degree. So tenth of a degree means one spot after the decimal place. So if we round this to their standards, is 36.6 degrees. Obviously that is rounded there. Okay, so that is using sine law to solve for a missing angle. Then within that same triangle, once you have the complete ratio, use sine law. Obviously, we could use cosine law a second time there, but it's unnecessary work if you can use sine law. It's usually a little simpler, more straightforward to use sine law.